Now, dear students, in this video, we will be trying to understand KiCad PCB layers and their functionality and their role in the PCB design process. So over here, you can see that we have a list of all the layers that are provided by the KiCad. So let's see which layers these are. The first one is the copper layer. Then we have adhesive layer. Then we have solder paste layer. Then we have silk screen layer. And then there is a solder mask layer. Then we have a user drawing layer, user comments, user eco 1 and eco 2 layers. Then we have edge cut layer, we have margin layer, and then courtyard layer. Then we have the fabrication layer, and then we have the user layer. So in the next we will be discussing these all the layers in detail. So let's just start with the copper layer. Copper layer, a layer of PCB that has copper on it after etching. Over here on this side you can see that these are the tracks that are drawn, and these are drawn in the copper layer. Usually tracks and pads or power and ground layers are made in copper layer. So all the routing that all the components that are connected with one another, and that uses the copper layer to make connection between the pins of all the components. If we are creating a single-sided PCB, the circuit board has one layer of conducting material on one side of the board, and the other side is used for incorporating different electronic components. So over here you can see this is a single-sided PCB, which means that it has copper layer on one side of the PCB, and we drew a hole through these PCB so that we can mount our components over here. And if we have a double-sided PCB, in double-sided PCB can mount the conductive copper and the components on both sides of the board. So over here you can see that we have copper tracks on the top as well as the bottom of our PCB, and we have just drilled the holes through the PCB, and in this way we can mount our component either on this top side or on the bottom side. Double-sided boards allow for closer routing tracks, as they can alternate between the top and bottom layers using vias. So in double-sided boards you can draw track from top to bottom. Let's say if we have some component on the top of the board and some on the bottom, then we can connect the top of the component with the bottom using vias. Over here in this picture you can see this is the via internal structure, this is the via physical appearance, how the via will looks. And over here this is a 3D view in which you can say, let's say if this is a trace on the top side of the PCB, you can drill via through the PCB, and you can attach with some other copper layer using again the traces. So in this way, if you have double layer or even multiple layers, you can connect the layers with one another or the tracks on the layers with the help of vias. Multi-layer PCB consists of more than two conductive layers separated by insulating material, typically made of epoxy and reinforced with fiberglass. If you are using multi-layer PCB, then what will happen that you have a copper layer, then you have a pre-preg layer or the epoxy or fiberglass layer, then again a copper layer, then again a pre-preg copper layer, then a pre-preg and a copper layer. In this way you can you can make a multiple layer PCB. The thickness of the copper layer on your PCB will depend on the power the PCB needs to withstand. PCB that needs to handle very high power have a thicker copper layer than those that do not. Majority of the PCBs are usually constructed using a copper thickness of 1 ounce. If we want to add more copper layers, then they use the name in and then the number of the layer and then .cu, which means that it is a copper layer, and it is done by default in the KiCad. It says that if you want to add more layers in your PCB while designing the PCB in KiCad software, then there will be two by default layers, the front copper and the bottom copper. and if you want to add more layers, then that will be named as in1, in2 layer in the KiCad. So the copper layer helps us to connect the components with one another in the PCB design process. The next layer is the adhesive layer. It is also the front adhesive and back adhesive. This is layer in multi-layer PCB stack up that contains adhesive material. This is used in flex and rigid flex board design to bind flex layers together in a board. Adhesive layer is usually epoxy resin which is activated during the lamination process. When the PCB stack is subjected to heat and pressure during lamination, the adhesive layer bonds the layer of prepreg and copper clad laminate together, forming a solid multi-layer structure. The adhesive layer plays a crucial role in ensuring the structural integrity and reliability of the multi-layer PCB. Every flexible circuit uses an adhesive in some form or fashion, either in the stack up or externally, which means that adhesive layer can be used between the layers, and it can also be used externally, so that you can also fix the component on the PCB using some adhesive material and then solder the components on their pads. Overall, the adhesive layer is an essential component of multi-layer PCB construction, contributing to durability, reliability, and performance of finished circuit board. Then the next layer we will discuss now is solder paste layer. Solder paste layer refers to layer used in fabrication process to indicate where solder paste should be applied for surface mount components. It says that when you want to stuff your component on the PCB, then you have to place solder. So this solder paste layer will specify where you have to apply the solder paste so that you can solder your component on this. Solder paste is a mixture of tiny balls of solder suspended in flux. It is applied to pads on the PCB where surface mount components will be placed. Like over here on the right side, you can see that these are pads on which solder paste is applied. So solder paste, when you will zoom in and you will see that it consists of tiny balls of solder that is suspended in the flux. And when you heat them, they reflow and make a connection between the PCB and the component. It typically shows the solder paste layer. It shows the outline of the pads for surface mount components with dimensions and position precisely defined according to the design requirement. So over here you can see that this is the front copper layer of the PCB that you are now seeing in the picture, and there are the pads over here, like this one is the pad, this is the pad, these are pad. So this is some IC that has pad over here. So what solder paste layer will be, that will indicate where we want to apply the solder paste so that we can connect our components over here. Like this is the front copper layer and this is the front paste layer, solder paste layer. This specifies the area to apply solder paste. So let's say if I want to stuff this component over here, I have to place the solder paste on these pads over here, and then I will place the component on it, and then I will heat this PCB, and that will bind the component and the PCB with the help of solder paste. So solder paste layer only shows the outline of the pads. During the PCB manufacturing process, the solder paste layer guides the application of solder paste onto the PCB using a stencil. The stencil is aligned with the solder paste layer, and solder paste is applied through the stencil onto the pad. So the solder paste layer, if you want to apply the solder paste on the PCB, what you have to do, you have to that the solder paste layer is also called a stencil layer because it will specify where you want to apply the solder paste. So you will create a frame, or you can say a stencil, in which there is an aperture layout. Then you will place this stencil onto the PCB and then apply solder paste onto this onto the PCB. Usually the size of stencil will be smaller than the actual pad on the circuit board. After the solder paste is applied, surface mount components are placed onto the pads and the entire assembly is heated in a reflow oven. The solder paste melts, creating a solder joint between the components and the PCB pad. Paste mask layer or the solder paste layer can also be divided into top paste or the front paste and the bottom paste. A solder paste layer in the rubber file is used to define the exposed copper pad features on bare boards in PCB manufacturing and is mainly used to customize solder paste stencil in PCB assembly. Thus, a solder paste layer is also called a stencil layer because this solder paste layer actually specifies where you want to apply the solder paste. So you can also make a stencil out of this solder paste layer. So next is the silk screen layer. This layer is very important in the PCB design process. PCB silk screen act as a communicative layer, providing essential information to various stakeholders involved in manufacturing, testing, and servicing of the board. Silk screen is a layer of ink traces used to identify components, test points, parts of the PCB, warning symbols, logos, and marks. Over here you can see that this white line around the resistor is actually the marking of the resistor that is done in the silk screen layer. Similarly, if you have designator along with this rectangular of the resistor, this is the reference designator. Similarly, if you can see over here, this is the pad for and ground, and you can see you have written in silk screen this G and D, which means ground. And over here you can see capacitor silk screen. Similarly, these white markings on PCB is silk screen helping to identify the parts. The silk screen layer aids in assembly process, guiding the placement of component on the PCB. It helps ensure that components are correctly and consistently placed, reducing the risk of error during assembly. You can see this is the actual PCB, and if I want to separate only the silk screen from this PCB, that will look like this. In the silk screen you will see that you have this marking of the capacitor C14, its indication that which side is positive. Similarly, you can see over here that is diode which says D15, and in this way you can identify that which component in your schematic is placed at which place in your PCB. So silk screen helps to actually communicates with us that the components that you have specified in the schematic are physically placed in the PCB. This silk screen is usually applied on the component side. However, using silk screen on the solder side is also not uncommon. This means that you can apply the silk screen on the front side as well as the back side, towards the component or towards the soldering side of the component. The position or where the layer ink traces are made is very crucial to identification of components, letters, number, and other key signs and symbols on the circuit board. Essentially, a detailed PCB silk screen can help both the manufacturer and the engineers to locate and identify all the components. The ink used for this marking is a non-conductive epoxy ink. The marking that we do on the PCB, that ink is a non-conductive epoxy ink. The standard colors are we normally see are black, white, and yellow. PCB software also uses standard fonts in silk screen layer, but you can choose other fonts. A silk screen can provide the following information. It can tell you the polarity of the parts. Like over here you can see that it is C1 capacitor with the reference designator C1 and has plus sign on this side. The next thing is the location of the part through reference designator. Like over here you can see this is U1. The U1 IC will be soldered or stuffed over here. The next thing is identify test points. Like over here, this is some point you can test, is a test point over here, like test point over here. And the identification number unique to each board. Let's say like over here it is written that it is the video, which means that it has this board is something that is related to video section. So in this way, silk screen help us to communicate with us. It tells us about the polarity, location, identify the test point, and identification number of each board. It also helps us the warning symbols you can even add on your PCB using the silk screen layers. The next is solder mask layer. Solder mask or solder resist is a thin lacquer-like layer of polymer that is usually applied to copper traces of a printed circuit board for protection against oxidation and prevent solder bridges from forming between closely spaced solder pads. Over here you can see this green layer. It's actually the solder mask layer. It is covering the tracks. Over here, this one, the track between these both the pads is covered with the polymer, this solder mask layer. This will help this track from oxidation, and this solder mask also help us to prevent solder bridges from forming between closely spaced solder pads. A solder bridge is unintended electrical connection between two conductors by means of small blob of solder. Over here you can see that this is the solder bridge, that two pins are shorted with the help of solder. Like over here, this is some solder bridge. This is the solder bridge. The primary objective of applying a mask is to eliminate undesired electrical connections between the copper features. Solder resist is a protective layer that insulates the conductive traces and shields them from environmental contaminants such as moisture and dust. It typically comes in different colors. Mainly you can see in a green color. However, other colors such as red, blue, and white are also available. So you can see a PCB of different colors like green, red, blue, and white. These are actually the solder mask. That coloring is done in the solder mask layer. The next is user drawing layer. User drawing layer is a customizable layer that allows user to add their own drawing annotations or other graphical elements, dimensions, and other information to the PCB layout. This layer enhances the flexibility and usability of the KiCad PCB design software, allowing designers to create more informative and visually rich PCB layout. User drawings layer provide flexibility for users to add additional information or visual cues that may not be represented in standard layer provided by the KiCad. So in drawing layer, you can add different types of drawings on your PCB. Here are some key points about the user drawing layer. The first is custom annotation. User can add custom annotations, notes, or labels to the PCB layout using this user drawing layer. Then we can add graphical elements. User can draw shapes, lines, arcs, or other graphical elements directly onto the PCB layout using the user drawing layer. Then we have dimensions and measurement. User can add dimensions and measurement to the PCB layout using the user drawing layer. Then masking and overlay. The user drawing layer can be used to overlay or mask certain areas of PCB layout. This can help user visualize the layout more effectively or hide specific features during different stages of design process. The next layer that we will discuss now is the user comment layer. User comment features allow user to add text comments directly onto the PCB layout. Like over here, you can choose on the right side user comment and then add a text over here, and you can add directly onto your PCB in the user comment layer. These comments are typically used for documentation purpose, providing additional information about specific components, design choices, or other aspects of the PCB layout. Over here you can see that in the previous slide we have added comment in the PCB editor, and now in the 3D view you can see that this comment is added over here on this 3D view of the PCB. User comments in KiCad serve as valuable tool for annotating PCB layout, facilitating collaboration among team members, and ensuring that important information is communicated effectively throughout the design process. Now we will discuss the next layer, that is user Eco1 and Eco2. In KiCad, the layers user Eco1 and user Eco2 are part of user definable layers that offer flexibility in adding custom information or annotations to the PCB layout. While their name suggests a potential focus on economics or ecological aspects, their use is entirely up to the designer's discretion. The user eco layer provides designer with flexible tool for incorporating economic consideration into the PCB design process, helping to ensure that cost-effective design decisions are made and documented effectively. Then the layer edge cut layer. This is very important layer because the edge cut layer in KiCad, also known as the keep out layer, is used to define the outline or shape of printed circuit board. In the edge cut layer, you first of all select the edge cut layer and draw any box that will actually define the boundary of your PCB. It specifies the physical boundary of the PCB and determines its final shape and dimension. Breakdown of its key characteristics and uses are defining board outline. The primary purpose of edge cut layer is to define the outline of the PCB. Designers draw the board outline on edge cut layer to specify the shapes of the PCB, including its outer edges, cutouts, cut corners, and any other feature required for the board's form factor. Mechanical dimensions. The edge cut layer also include mechanical dimensions and annotations related to physical dimension of the PCB. This information helps ensure that the PCB meets the mechanical requirement of the enclosure or housing it will be installed in. Keep out areas. Designers can use the edge cut layer to define keep out areas where components, traces, or other features are not allowed to be placed. Keep out areas are essential for preventing interference with mounting holes, connectors, or other mechanical features on the PCB. Panelization. When manufacturing multiple PCB on single panel, the edge cut layer defines the boundary between individual PCBs. Designers can specify the location of routing tabs, fiducial marking, and other features required for panelization on this layer. Then we can add manufacturing constraints. The edge cut layer serves as a reference for PCB manufacturer, providing guidance on where to cut or route the PCB during the manufacturing process. It helps ensure that the final PCBs are produced with the correct shape and dimensions according to the design specification. Next, we will discuss the margin layer in the KiCad. In KiCad, there isn't a specific layer called the margin layer by default. However, designers often use the term margin to refer to keep out layer or clearance areas around the edges of the PCB or around specific components. These areas are used to ensure that there is enough space for assembly handling and other consideration. The term margin is typically used in PCB design for edge clearance. Designers might specify a margin on the edge of the PCB layout to ensure that there is sufficient clearance between the board features such as traces, pads, or components and the board edges. Component clearance. Designers might define margins around specific components or group of components to ensure that there is enough space for assembly, soldering, and maintenance. These margins help prevent solder bridges, mechanical collisions, or other assembly issues. Keep out areas. Margin areas may also be designated as keep out zones where no component traces or other features are allowed. Panelization margins. In panelized PCB designs where multiple boards are manufactured on a single panel, designers might specify margins between individual PCBs to facilitate separation during the depanelization process. These margins ensure that there is enough space between adjacent PCB for cutting tools or equipment. So margin layer helps us to make a keep out areas. It all helps us in panelization of the margins. The next layer we will discuss is the courtyard layer. This is very important layer. Courtyard is the area around a physical component required for assembly and other functional purpose. No other component should be placed inside that area. The courtyard layer actually helps us to specify the area around the component in which you cannot place any other component. Like over here, this is the physical component over here, and this is the courtyard layer. The component should be placed inside the courtyard layer. and no other component should overlap with this courtyard layer. A rectangle is often used as a courtyard, and in most cases one rectangular shape should be sufficient. So over here this is the landing pattern and body of the component, and this is the physical boundary of the component. Then this is the courtyard layer. Courtyard layer actually covers the entire component. It actually gives a little spacing between the physical boundary and gives an extra area so that someone can easily place the components in the assembly process. And over here, when the component is placed over here, there is a little area which is the courtyard layer. And over here you have to also add courtyard. This is the courtyard access, because you can also draw courtyard over here like this, but you have to give this, as you cannot place any component between the two legs of this component. So this is the courtyard access area. Overall, the courtyard layer just helps to give a little margin with the other components so that the footprints or the components don't overlap with one another. If components are too close to each other, assembly may be difficult or impossible. When discussing assembly, this really depends on the assembly style. Either you are assembling automatic assembling, or you are doing a manual assembly process. In KiCad, the courtyard layer is used to define the area around a component on a printed circuit board. This layer is essential for design process, as it helps ensure that there is enough space around each component to accommodate manufacturing tolerance, assembly process, and avoid any potential interference or collision between components. So now we will discuss the fabrication layer. In KiCad, the fabrication layer is used to convey additional information to the manufacturer or fabricator of the printed circuit board. This layer contains information that helps in fabrication and assembly process. Some common uses of fabrication layer in KiCad includes assembly instructions. Component placement, outlines, or assembly instructions can be drawn on fabrication layer to guide the assembly process. These outlines helps technicians understand where each component should be placed on the PCB during assembly. Special markings such as polarity indicators or orientation markers for component can be added to fabrication layer. These markings ensure that components are oriented correctly during assembly. Then is the board outline. The outline of PCB itself, including its shape and dimensions, can be defined on fabrication layer. This helps the manufacturer understand the physical boundary of the PCB. Reference designator, which are labels for components on the PCB, can be included on the fabrication layer. These labels help identify components during the assembly process. Then is the drill holes. Information about drill holes, including their location and sizes, can be included in fabrication layer. This helps the manufacturer understand where to drill holes for mounting components or for other purpose. The next layer is the user layer. In KiCad, the term user layer can refer to two things: general user layers or specific user layers like the F.Cu1 or the F.Cu2 user we have discussed previously. General user layer, KiCad provides general purpose drawing layers that are not predefined for specific functions in PCB manufacturing process. These layers are intended for you to add custom elements to your board designs that are not part of the electrical functionality or fabrication instructions. You can use them for things like adding internal documentation and notes directly on PCB layout, creating mechanical outline and drill holes, marking enclosures, including logos or other visual elements. Then is the user layer, specific user layers. KiCad also have some predefined user layers with specific purpose. For instance, the fabrication layer is commonly used for fabrication related information that is not part of the standard silk screen or solder mask layer. So it's up to you. The user layers are now given from 1 to 9, as you can see on the top right corner, that are provided in the KiCad. You can use as per your requirement. So there are almost 13 different types of layers in the KiCad we have discussed now. Let's just summarize the KiCad layers. The first one is a copper layer, in which we draw our tracks, pads, ground and power planes in the copper layer. If you have two layers, then there will be a front copper and bottom copper. If you add more layers, then the KiCad will name as in 1, in 2 coppers. The next is adhesive layer, that helps us to bind the flexible PCBs and the rigid PCBs together. Then there is a solder paste layer. This is the layer which specifies where the solder paste should be applied onto the PCB. Then we have silk screen, that helps us to identify the component with the help of reference designator. You can even add text to specify some test points, etc. on the silk screen. Then we have the solder mask layer, which actually covers specify that which section of the PCB should be covered, like the tracks are covered for with the solder masks to prevent the oxidation of the tracks. Then we have user drawing layer, where user can draw their custom things, add custom elements on the PCB. Then we have user commands to add comment on the PCB, user eco1 and eco2 to add economical things on the PCB. Then we have the edge cut layer. This is very important. It actually defines the physical boundary of the PCB. Then we have margin layer, which can be used for specifying the margins. Then we have courtyard layer, that actually specify the boundary of the component, or the component in which you have to place the component, and you cannot overlap the courtyard with any other component. Then we have fabrication layer, in which you can specify document your PCB, so that manufacturer can understand how you want to fabricate your PCB. Then we have the user layers, that you can use as per your desire, as per your requirement. The main layers that are very important in the PCB design is the copper layer, that is very important. Then we have silk screen layer, that is very important. Then we have edge cut layer, that is very important, and courtyard layer, that is very important. So all these layers that which I have specified are important, will fulfill the minimum requirement of your PCB. So hope you have understood all the layers that are present in the PCB, their functions and their roles in the PCB design process.